This video is about inverse hyperbolic functions. Here we're going to define the inverse hyperbolic functions. I don't think it's any surprise that inverse hyperbolic functions involve logarithmic functions. So remember how our hyperbolic functions are defined. The hyperbolic functions are combinations of exponential functions. So the hyperbolic sine of x is 1/2 of e to the x minus e to the negative x. And the hyperbolic cosine of x is 1/2 of e to the x plus e to the negative x. So that's an odd combination of e to the x and e to the negative x, and this is an even combination of e to the x and e to the negative x. Now it turns out that if I'm trying to undo this operation, it makes perfect sense that I would have logs over here. And the hyperbolic tangent, cotangent, secant, and cosecant are exactly what you would expect, knowing the definitions of the tangent, cotangent, secant, and cosecant functions from trigonometry. So in this video, we will look at these definitions, we will prove one of these definitions, and then if you want to, you can prove the others using the same method. We'll talk about finding the derivatives to these functions, and then some antiderivatives, which will just be the derivative rules for these in reverse. So let's think about what this inverse hyperbolic sine function really is. Now the hyperbolic sine function actually looks like this. We looked at this in the last couple of videos. It's 1/2 of e to the x minus 1/2 of e to the negative x. So as x goes to infinity, this term approaches 0, and that hyperbolic sine of x approaches this function, y equals 1/2 e to the x. In fact, it gets very, very close to that, almost infinitely close. It looks like, it's almost like we're approaching it as an asymptote. It's not what this is, because asymptotes are lines, but it's very similar to that. And it turns out that that hyperbolic sine function will always be just a little bit less than this one, and that amount less that it is in this one is this amount over here. So it's like we're taking these y values and we're adding these negative y values. And so when we take that and we subtract that much, we end up with this function here. Now as x goes to negative infinity, this term approaches 0, and then this piece approaches infinity. So the hyperbolic sine function goes to negative infinity on the other side. But I think more importantly, this hyperbolic sine function approaches this function almost like an asymptote. But again, it's always just a little bit more than that. And that little bit more is coming from the y values on this function. So if we take the y values on this function and we add the y values on this function, we get the y values on the red function. Now to graph the inverse hyperbolic sine, we need to switch the roles of x and y here. So here where I had the curve y equals 1/2 e to the x, I needed to draw the curve x equals 1/2 e to the y. That's just switching the roles of x and y on that equation. And if we do that, what we see is we see that same curve, but flipped. It's sort of reflected across the line y equals x. So we see that curve over here. And if you're saying to yourself, that doesn't look like an exponential, it looks like a logarithm, you're absolutely right. Because if I solve this for y, let's see what we get. We have 2x equals e to the y. And to get rid of the exponential, I'll take the log of both sides. So this is actually y equals natural log of 2x. That's what that's equivalent to. So y equals natural log of 2x and y equals 1/2 e to the x. Those are inverse functions. They undo each other. Or you could just take this equation, switch the roles of x and y, and you get an equivalent equation. You get the inverse function there. So I wrote the inverse function for this. That's there. And then the inverse function for this is x equals negative 1/2 e to the negative y. That's this one. Forgot to put my negative sign there. So when I switch the roles of x and y, there, these are going to serve kind of like asymptotes, just like these two functions serve over here. for the inverse hyperbolic sine function. So we switch the roles of x and y here, and we get something that looks roughly like this. And that is the graph of x equals hyperbolic sine of y. So I'm switching the roles of x and y. And then if I want to solve for y, all I have to do is take the inverse hyperbolic sine of both sides. So this is y equals the inverse hyperbolic sine of x. So remember, that's how inverse functions work. You're just switching x and y because these are two functions that undo each other. This one goes from x to y. When we do the inverse function, we want to go from y back to x. So that's why we switch. Okay, so this is the hyperbolic cosine function. If you prefer, you can call it cosh x. Now, if I want to find an inverse function for this, it's not going to work. It doesn't have an inverse function. You see, it doesn't have an inverse function because that red graph fails the horizontal line test. A function has to pass the horizontal line test to have an inverse function just directly in its current form. If I switch the roles of x and y over here, this graph, which looks a little bit like a parabola, it's not a parabola, but it looks a little bit like a parabola, would be turned on its side, and I would see that graph over here. Well, if this fails the horizontal line test, when I switch x and y, the resulting graph will fail the vertical line test and it won't be a function. So we've got to restrict this somehow. The generally accepted restriction of the hyperbolic cosine function is this part of the function. So we look at the restriction of the hyperbolic cosine function on the interval from 1 to infinity, and then we switch the roles of x and y. So instead of drawing this curve and this curve, I just drew the inverse of y equals 1/2 e to the x, which is x equals 1/2 e to the y. As we saw up here, that's equal to y equals, or that's equivalent to y equals natural log of 2x, which I think makes sense that the inverse of that function is this function. And then when I switch the roles of x and y on my hyperbolic cosine function, I'll get this. It looks like that. If I were to switch the roles of x and y for the whole thing, I would get something that's sort of this. It would look almost a little bit like, well, it would look like a branch of a hyperbola almost. Looks like a parabola facing to the right. But we don't get the whole thing because that wouldn't be a function. We just get that part. We switch the role of x and y on that part and we get this part. Now this crosses the y-axis when y equals 1. So when we switch the roles of x and y, this graph crosses the x-axis when x equals 1. The domain of this one was all real numbers and the range was 1 to infinity. Now our domain is 1 to infinity and the range, due to the restriction, is 1 or 0 to infinity. So this red graph is the inverse hyperbolic cosine graph. It's x equals the hyperbolic cosine of y, but we're requiring well, actually, let's solve this for y. Oops, I'm sorry. The inverse hyperbolic cosine of x equals y. So if we take the inverse hyperbolic cosine on both sides, the inverse hyperbolic cosine of the hyperbolic cosine just gives us y, and then we have the inverse hyperbolic cosine of x equals y. So this is our graph, but there is a restriction. We're saying that x is equal to a hyperbolic cosine of y, but we're requiring y to be greater than or equal to 0, and we're requiring x to be greater than or equal to 1. So their domain is 1 to infinity. Okay. And those y values are going to be 0 to infinity, not negative infinity to infinity like we might expect from over here. Okay, and then for the hyperbolic tangent function, we get this graph. If it looks a little bit like the inverse tangent function, you're right, that's a shape. Kind of. It's not exactly the same, but it's kind of like that. But remember how this is defined. It's the hyperbolic sine of x over hyperbolic cosine of x. After we reduce those 1/2 that exist in both formulas, we get something like this in terms of our exponential functions. As x goes to infinity, these terms go to 0, and this hyperbolic tangent function approaches e to the x over e to the x, which is 1. So we get very close to this line. And as x goes to negative infinity, these terms go to 0, and so we approach this negative e to the negative x over e to the negative x. So we get -1 on that side. So it looks a little bit like an arctangent. It's not an arctangent, but it has a similar shape. But the asymptotes are y equals -1 and y equals 1. Now, if we switch the roles of x and y here, these horizontal asymptotes, y equals -1 and y equals 1, become vertical asymptotes, x equals -1 and x equals 1. And then if we switch the roles of x and y here, we get a graph that looks roughly like that. So this is y equals the inverse tangent of x, or x equals the, or I said inverse tangent, this is y equals the inverse hyperbolic tangent of x, or x equals the hyperbolic tangent of y. And it turns out that that's equal to this. Since the range of this one was -1 to 1, and it did have an inverse function as it's drawn here, and it passes the horizontal line test, so we have an inverse. This is its inverse. Since the range here was -1 to 1, the domain here is -1 to 1. Since the domain here was negative infinity to infinity, so the inputs, the x values, were going from negative infinity to infinity. When you switch the roles of x and y, the outputs, or the y values, go from negative infinity to infinity. So those are our graphs. I'm not going to look at the inverse graphs for the other three functions, but I would like to prove to you now how the inverse hyperbolic sine of x is actually equal to this function. So let's look at that. And remember how you did this back in your pre-calculus class. If you wanted to show, or if you wanted to find the inverse function for a given function, usually you just stated y equals the function that you're looking for. In our case, that's 1/2 e to the x minus e to the negative x. And then you would switch the roles of x and y and then solve for y. And the reason that worked is because these are inverse functions. Because this is basically the idea. If xy is on the point, or is a point on the graph of f, we're thinking of this as a map. F takes x and it maps it to y. If we're trying to undo that operation with f inverse, my f inverse graph has to take y, that result that we just found, and map it back to x. So if x goes to y and I'm trying to undo that, then I go from y back to x. The point xy is on this graph if the point yx is on this graph. And it's because of what we're trying to do. We're trying to undo that initial operation. So we have y is equal to this function. If I want to find the inverse function associated with this function, we switch the roles of x and y. So we replace the y with an x, and we replace the x with a y. And now your goal is to solve this equation for y. You want to get y by itself. Now on the surface, it looks like it's a difficult thing to do. It's not too bad. You just have to think about this a little differently. I'll show you how to find y in just a second. The easiest part of this problem is getting rid of this 1/2. We're multiplying by a 1/2 here. So to undo multiplying by 1/2, we'll multiply by 2. Multiply by that reciprocal. And that will get these exponentials by themselves. Now, one problem with this is that I've got an e to the y and an e to the negative y. I'd rather not have that. I'd rather have just an e to the y or an e to the 2y. I don't like having this negative exponential because it makes it a little bit more difficult for us to solve. So what I'm going to do to get rid of this e to the negative y is I'll multiply both sides of this equation by e to the y. And watch what happens. On this side, I've got 2x times e to the y. On this side, I've got e to the y times e to the y, which we could call e to the 2y, or if you prefer, and I do prefer it, I want to call that e to the y squared. And this e to the negative y times e to the y can be simplified this way. You just add the exponents. Negative y plus y is 0, so that's e to the 0, which is 1. Do you see it? It's quadratic in e to the y, even though it doesn't look like it. If it's not obvious to you, let's subtract that e to the, or that negative 2x times e to the y from both sides. And so we have 0 equals e to the y squared minus 2x times e to the y minus 1 equals 0. And that's quadratic. It doesn't look quadratic, but it's quadratic. If I think of this as my variable, I've got a variable squared minus 2x times the variable minus a variable. So this can actually be solved using the quadratic formula. I know it doesn't look quadratic, but it is. It's quadratic in form. It's just instead of having an x here, I've got an e to the y. And instead of just having a constant here, I've got a 2x. But I can solve this the same way that I use, or that I solve a quadratic formula, or a quadratic equation, excuse me. So remember how that works. If we have an equation like this has two solutions. The two solutions are given by x equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. We're going to do the same thing over here, except our a, b, and c are going to be allowed to depend on x. So our a is 1, our b is negative 2x, and our c is negative 1. And instead of an x, we're going to use e to the y. And if you prefer, if you don't like this, you feel like that looks really complicated, you can make a substitution. Just let u equal e to the y, and then you'll see this. It still looks bad because of that minus 2x there, but it makes it a little bit more obvious that that's quadratic in form. I've got u squared minus 2x times u minus 1. So according to the quadratic formula, u is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. And our a is the coefficient of u squared. So that's 1. It's 4ac. B is the coefficient of u, which depends on x, and that's fine, actually. This still works. So b is negative 2x. This is negative b plus or minus the square root of b squared minus 4 times a times c, which is negative 1, all over 2a. Let's simplify this and solve for u. A negative 2x is positive 2x. Over here we've got this, which is a product squared, so we can square both factors separately. then I'm subtracting 4 and I'm multiplying by -1, so that's the same as adding 4. We're dividing all of this by 2. Okay. I can factor out a 4 from that x squared, or that 4x squared and that 4. And the benefit I see in doing that is now I can take the square root of this factor and the square root of that factor separately. And I see that I'll have a 2 there and a 2 there, and everything will be divisible by 2. So this is going to work out really nicely. So I've got u equals 2x plus or minus 2 times the square root of x squared plus 1, all divided by 2. And if you want, you can factor out a 2. Those 2's reduce. And that's equal to our u. So if u satisfies this equation, then u has to be equal to x plus or minus the square root of x squared plus 1. Now remember what u was. U was actually e to the y. We're trying to get y by itself. I know it's hard to even remember what it was we were doing. We're trying to find the inverse function for the hyperbolic sine of x. And the way we decided to approach that was we wrote y equals this function, and then we switched the roles of x and y, and now we're trying to solve for y. So we got down here, we got to this point, we had something that was quadratic in form, we got this, and now I've got u equals this. But remember what u is e to the y. And remember, we're trying to get y by itself. Now, this plus or minus actually gives us 2 solutions. That corresponds to 2 different equations. We have u, or e to the y, equals x plus that positive, or plus that square root. And then over here, we have e to the y equals x minus that square root. Okay, now if I'm trying to get to y, and I have an e here, I need to take the log of both sides to get rid of the e. Because the natural log and that natural exponential function undo each other. And you see, that means that y has to be natural log of x plus the square root of x squared plus 1. And remember what y was. We have y equals hyperbolic sine of x, and then we switch the rules of x and y. When we switch the rules of x and y, what this equation was equivalent to is x equals hyperbolic sine of y. Or if we take the inverse of both sides, we'll have the inverse hyperbolic sine of x is equal to y. So we did all of this just so that we could figure out what y was, and y is the inverse hyperbolic sine function. So it turns out that the inverse hyperbolic sine function is this, because the original hyperbolic sine function was this. When we switch the roles of x and y and do a whole lot of algebra, which included solving this equation that was quadratic in form and had variable coefficients for e to the y, and then back substituting, we see that if the hyperbolic sine of x is defined to be 1/2 e to the x, that should be a minus e to the negative x, then to undo that, we're going to use a log, the inverse hyperbolic sine of x plus the square root of x squared plus 1. That will undo that. And it makes sense. If I use exponentials when I'm defining this function, to undo that, I would expect to use logarithms. Now, what about this equation? Now, you might be saying to yourself, well, that should be a second solution. We should have 2 parts to the inverse hyperbolic sine function, this one and this one. But actually, this one doesn't work, and let me tell you why. the square root of x squared plus 1 is always greater than the square root of x squared. And the reason that it's always greater than the square root of x squared is because you have this plus 1 under the radical. There's just a slightly larger number under the radical here than there is here. So what does that mean? Well, if we're talking about positive x values, the square root of x squared plus 1 is greater than x. And that means the square root of x squared plus 1 minus x is greater than 0. And if I multiply both sides of this equation by -1, I get x minus the square root of x squared minus 1 is less than 0. So if I multiply this side by -1, I change that order. And multiplying an inequality by -1 changes the direction of that inequality. So you might be saying, so what? What does that mean? Well, remember, this is an exponential function. This is e to the y. E to the y is a function that looks like this. It's like this is x equals e to the y. That's what that function looks like. The values of that function are always positive. Well, the x values on this graph are always positive. I hope you see that. Or you can think of this as the output of an exponential function. Exponentials only give you positive numbers. No matter what y is, this is a positive number. And unfortunately, that's a negative number. So this does not have any solutions. So these have to be the inverse functions, this has to be the inverse of this. So we just solved for the inverse function algebraically. Let's confirm it by doing one more thing. If these are truly inverse functions, you should be able to do the following. Inverse functions undo each other. So if I apply the inverse function to f, and I get some output, and then I apply the original function to that output, I should get x back, because this is going from x to y, and then this function is supposed to go from y back to x because of the way they undo each other. So this should be x, and it should also work the other way around. F of x is a map. It goes from x to y. F inverse goes the other way. It goes from y back to x. So we can think of going from x to y and then y back to x, if you want. So this should give me x back, because these two functions undo each other. Maybe I should draw my picture this way. Here's x and here's y. F goes in that direction. F inverse goes in that direction because they're undoing each other. So if I apply this to x, and then I take f of the result, I should get x back because they undo each other, and vice versa. So I just did a bunch of algebra to prove or to derive this formula for the inverse hyperbolic sine of x. Let's prove that by showing that f of the inverse hyperbolic sine of x is x, and it also works the other way around. Maybe we'll just do one direction. I'll let you do the other direction in your homework if you'd like. So let's look at the hyperbolic sine of the inverse hyperbolic sine of x. So I'm going to show that this is true. That's what I want to show. And through the notation, you might say, oh yes, of course, the sine and the inverse hyperbolic sine undo each other and you get x. That's true, but we're trying to prove that using these functions. So what I'd like to do is take that hyperbolic sine function, which is this, and everywhere I see an x, I want to replace it with the natural log of x plus the square root of x squared plus 1. If this is truly the inverse function for the hyperbolic sine, I should get x back when I'm done. So we have the hyperbolic sine of this, that's 1/2 of e to that power minus e to the opposite of that power. We get this over here. And now we've got to use some log properties and exponential properties to simplify this. Well, e raised to the natural log of a power just gives me a, because e and the natural log are inverse functions. They undo each other. So we end up with 1/2 of x plus the square root of x squared plus 1 right here. Now over here, it's not as simple. You can't just cancel that e with that log because of that negative sign. So we have to use this other property first. Remember this property, n times natural log of a equals natural log of a to the n. You can bring that up as a power inside, or we've often taken that power and brought it outside. We can do that here. That's a -1, needs to be brought up as a power inside. So this is minus e to the natural log of x plus the square root of x squared plus 1, all raised to the -1 power. Okay, so the e and the natural log undo each other, and now we've got 1/2 of this minus this function to the -1. It's still looking pretty complicated, but I promise you it's going to give you x back in a second. Okay, so we're here. I've got this raised to the -1 power. So I can write that this way. That's minus 1 over that function. Still not looking like an x. I know, I get it, I'm with you. But if we get a common denominator, hopefully it will look like an x. So let's see what happens when we get a common denominator. I'm going to think of this first function as itself over 1. And then I've got this over here. Now, if I want to get a common denominator, the least common denominator of 1 and this denominator is just that denominator. So I'll multiply this fraction by x plus the square root of x squared plus 1. That's that function over itself. Now I want to think of this as a binomial times a binomial. I'm going to write it twice in FOIL. And now they both have the same denominator. So I'll write that in here. Let's do it. So first times first is x squared. Outer times outer is x times the square root of x squared plus 1. Inner times inner is just like it. Oops, I'm gonna need more space. Let's make that the bar a little bit longer. Last times last is that square root times itself. We're gonna get x squared plus 1 there. The square roots will undo each other. And then don't forget to subtract that 1 from over there. The 1's reduce. And now I've got an x squared and an x squared. So that's 2x squared plus this and that. Those are the same, so I've got 2 of those. You guys see it coming? It's a lot of algebra. Factor out a 2 and an x. We've got a 2 and an x in common in the numerator. Say 2x times what gives us that 2x squared, it's just an x. And then 2x times what gives us that? That's square root of x squared plus 1. And what do you know? check it out. Those reduce, the 2's reduce, and we get x. So the hyperbolic sine of this is equal to x. Now, if we did it the other way around, we evaluated this function at the hyperbolic sine of x, and remember that the hyperbolic sine is defined in terms of those exponentials, we should get x as well. I said I wasn't going to do it, but I want to do it. Let's do it. So we've got this natural log function. I want to evaluate it at the hyperbolic sine of x. But remember what hyperbolic sine of x is. Hyperbolic sine is 1/2 of e to the x minus 1/2 of e to the negative x. I just chose to distribute that there. In these parentheses, I think I'll just leave it factored. Okay, let's watch what happens. So here I've got 1/2 e to the x minus 1/2 e to the negative x. And then I've got all of this under the radical. If I square this, I get 1/4. If I write that twice in FOIL, I'll have e to the 2x minus 2 plus e to the negative 2x plus 1. Watch this. If we distribute that 1/4 through to everything, we have 1/4 e to the 2x, and that 1/4 times negative 2 is negative 1/2, plus 1/4 e to the negative 2x, plus 1. But adding that 1 to this negative 1/2 just changes the sign. It changes that negative 1/2 to a positive 1/2. And that's a clue, because now this looks almost identical to what I had before. I just changed the sign. So what that means is that must be this. And this is a perfect square. And that is e to the x plus e to the negative x squared. Now I can take the square root of this factor and this factor. So the square root of the 1/4 is 1/2, and then I have an e to the x plus e to the negative x. Distribute that 1/2. Okay, you see it? Okay, those guys reduce. And I've got 1/2 of this and 1/2 of that, so that means I've got one of those. Cool. Natural log of e to the x is x. So these functions undo each other. So we found this algebraically, and then we were able to prove that these are inverses by showing that these operations are true. This just basically means that they undo each other. F takes x to y, and F inverse takes y back to x. Since these are satisfied by these two functions, since we get x back and x back, we know that those are inverses. Okay, now the derivatives of inverse hyperbolic functions are basically found by taking the derivatives of the corresponding logarithmic function. I'm not going to find the inverse functions for the hyperbolic cosine, hyperbolic tangent, hyperbolic cotangent, hyperbolic cosecant, and hyperbolic secant. But I've stated them here, and you can find those in the same way that we found the inverse hyperbolic sine function. But if I want the derivatives for these guys, I'll just take the derivatives of those functions on the right-hand side. So the derivative of the hyperbolic sine function is the derivative with respect to x of the natural log of 1 plus, or x plus, that x squared plus 1 to the 1/2 power. Oops, it's on an angle, sorry. So this is my inside function. The derivative of log of a function is 1 over that function times the derivative of the inside by the chain rule. Now the derivative of x is 1, and then the derivative of this requires the chain rule. So we get 1/2 of the inside function raised to the negative 1/2. You substitute the inside function back in, and then you multiply by the derivative of the inside of that one. Derivative of the inside of that is 2x. So I've got that now. The 1/2 and the 2 reduce, and this is what we get. I've got 1 over x times, or plus this square root, times this. It's 1 plus x over, and that's an x squared plus 1 under a radical in the denominator. Now, one way that we can simplify this is to get a common denominator here and then just distribute. So I will write this 1 as a square root of x squared plus 1 over a square root of x squared plus 1. And that's actually pretty cool, because then we've got something up here and that reduces. It'll look a little bit better when I get that common denominator. So that numerator is the square root of x squared plus 1 plus x, and that's exactly what we have in this denominator. So those reduce, and we find that the derivative of the hyperbolic sine function is this. Or excuse me, that's the derivative of the inverse hyperbolic sine function. And you might remember that the derivative of the arcsine function looks very similar. Oops. It's close, isn't it? It's the same, almost, but there's a different sign there. Okay, we can go through that, go through this for each of these functions and find the derivative rules. And what we'll find is that the derivatives look very similar to the derivatives for the arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant. These are the inverse functions for the hyperbolic functions. And they're very similar to the derivatives are very similar to the derivatives for the inverse trig functions. But there's always these signs that are a little different. Like that has an x squared plus 1. This is a 1 minus x squared. So we can't really rely on any memory devices because the signs, the SIGN signs are off. I'm not going to hold you responsible for this. I actually don't know anyone in math that has the derivatives of the inverse hyperbolic functions memorized, but those are in your book. Feel free to look them up and then use them to take derivatives. So we've got the inverse hyperbolic sine derivative, which looks a lot like the derivative of arcsine. It's just a little different. Just different enough for our intuition to be completely incorrect. And then the inverse hyperbolic cosine derivative can be found using a similar method. And we didn't derive this formula for the inverse hyperbolic cosine. But knowing what we know about that last one, the derivative that led to this result, I think we can predict how this is going to go. Our inside function here, that is our inside function. When we take the derivative, we'll use the chain rule. That's 1 over the inside function times the derivative of the inside by the chain rule. And the derivative of the inside is 1 plus the derivative of this piece, which is 1/2. I'm going to write it as a fraction. 1/2 times this function to the negative 1/2 power. That's the same thing as putting that function in the denominator with a 1/2 there. Put the inside function back in, and then multiply by the derivative of the inside. The derivative of the inside is 2x. The 2's reduce. Now I need to get a common denominator, so I'll multiply this 1 by x squared minus 1 to the 1/2 over itself. And watch what happens. In the numerator, we have that x plus x squared minus 1 to the 1/2 again. And in the denominator over here, when we get a common denominator, we've got that square root of x squared minus 1. Oops, that should be an x squared minus 1. Ooh, that looks a lot like that arcsine derivative, but it's x squared minus 1 instead of 1 minus x squared. We can keep going with these guys. The inverse hyperbolic tangent turns out to be 1/2 of the log of 1 plus x over 1 minus x. If I'm taking that derivative, I would recommend bringing the 1/2 out and using log properties. That's log of a over b. So we can call that log of the numerator minus log of the denominator. The derivative of that is 1/2 times 1 over the inside function times the derivative of the inside, which is just a 1, minus 1 over the inside function here times the derivative of the inside, which is a negative 1. So we're going to end up adding those together. Now, if you get a common denominator here, so we'll multiply this one by 1 minus x and multiply that one by 1 plus x. Watch what happens. In my numerator, I have 1 minus x plus 1 plus x. And in the denominator, we have that 1 minus x squared. The x is reduced, and then I have a 2 in the numerator and a 2 down here, so those will reduce. And we still end up with a 1/2 of 1 over or 1, I said 1/2. We end up with a 1 over 1 minus x squared. And the derivative of arctangent is just like this, but with a positive x squared here. So you see it's very similar. They're very similar rules to our inverse trig rules, but they're just different enough to be wrong. All of our inverse trig rules are not quite what they need to be in order for us to use these. So those are the derivative rules for the first 3. I'm not going to do all the other 3. And then of course we've got corresponding antiderivative rules. So if I have the antiderivative of x squared plus 1 like this, that turns out to be the hyperbolic or the inverse hyperbolic sine of x plus c. And the antiderivative of this guy, that turns out to be the inverse hyperbolic cosine of x plus c. And the antiderivative of this guy is the inverse hyperbolic tangent of x plus c. In Calculus 2, though, we're going to learn some other techniques. I would almost never use the inverse hyperbolic sign for this antiderivative. I would use a technique called partial fraction decomposition to do that. And for both of these antiderivatives, I would probably use a method called trigonometric substitution that would get me answers in terms of logs, which are more familiar to us. But those logarithmic expressions can be written in terms of inverse hyperbolic functions. And again, the reason that these are actually logarithms is because the hyperbolic functions are actually combinations of exponentials. So those are the definitions, the derivatives, and the antiderivatives. You're not responsible for memorizing any of those. If you need those to take derivatives or antiderivatives on a quiz or a test in our class, they will always be given to you. But yeah, I just wanted you to see these functions and where they come from.